Assalamualaikum warahmatullah. So today is our lecture 11 and we'll be discussing the concept of projection today. Okay. So what is projection? So I think I already discussed the concept or the brief idea of projection in the discussion class. So that is, let's say you are in a 3D space and you have a vector and you want to find the reflection of the vector on different subspaces like this z axis, like this xy plane, right? So this is called projection. Find the reflection. If I try to explain it with the concept of a light source, let's say you have this straight line and there is another straight line here. So if you put a light source here, so the shadow that is occupied by this straight line, this part is called the projection of this is, let's say this is A and this is B. So this part here, the shadow here, is called the projection of A. Alright. Okay, so this projection is an important idea of linear algebra, because there when you solve, so we learn to solve Ax equals to B, right? And we could solve B only when B is in the column space of A. We could only find a solution for this equation if B is in the column space of A, right? But there might be a case where B is not in the column space, so Ax equals to B doesn't have a solution. So in those cases we find, so when B is not inside the column space of A, we find A x cap equals to P, where P is pseudo B, alright, like the projection of B onto the column space of A. We will see it in the later portion of the lecture, and X is the solution for it. So this is the closest solution. This is also known as the closest solution for X equals to P. So whenever B is not in the column space, we try to find the closest solution, and that's why we need projection, right? So there are many applications for this projection and this approximate solutions. So we'll see it in the discussion class. I will discuss one particular topic that is used very frequently in data science and linear algebra. So let's take an example to find the mathematical direction. Okay, so suppose there is line A that goes through the origin. This is line A, and there is another line B that goes through the origin but goes to some other direction, right? So let's say their difference is theta, and I want to find the projection of B onto A. So let's say there is a straight, there is a light source here, So what would be the projection? So the projection would be this, right? So now let's say the length of the projection here, the length of this projection here is P, and the difference here, the difference of A and B is simply known as the error E. Error E is equals to B minus P. So this is the difference between B and A. Okay. So you can see it from this line that the B is this E and this A, or this E and this P is perpendicular to each other, right? So okay, we'll get back to it later, but let's find a formal definition for P. So P is some part of A. So let's say there is some x, there is some fraction x that if you multiply x with the whole of A, you will get this P. Alright. So we have three goals. So let's define the goals here. So the goals are, you need to find the x cap, that particular fraction that multiplies, that is multiplied with A and results the projection P. The second goal is to find the projection. We need to find the projection P. So if you find x, you will automatically find P, this P. And the last thing is the projection matrix P. So projection matrix is such a matrix that if you multiply B with this projection matrix, you will be landing on this P. Okay, that so projection matrix, the matrix that causes the projection. Okay, so from this part here, E equals to B minus P, we saw that E equals to B minus x cap A, because P has the value of x of A, x cap into A. But from the picture here we can see that they have this A and this E have a orthogonal relationship, right? That means A into E, or A dot product E, is equals to 0. If two vectors are orthogonal, the dot product is 0. So from here we can write A into B minus x cap A equals to 0. So these are all dot products. So this can also be written as A into B, A into B minus x cap into A into A. So these are all dot products, okay, equals to 0. So I can write this as A transpose B minus x cap into A transpose A equals to 0. So what is the value of A from here? So the value of x from here. So the value of x is basically A transpose B divided by A transpose A. So this is the value of x cap. So our first goal here is achieved. So what is our second goal? We need to find p. So p is basically x cap into a. So x cap is basically a transpose b divided by a transpose a into a. So this can also be written as a into a transpose b divided by a transpose a. So this is our p, small p. So this is small p, that is achieved. So this is our second goal. So the last part is you need to find the projection matrix. So as I said, so what is the characteristic of the projection matrix at the first place? So as I said, that projection matrix is such a matrix that if you multiply this b with this projection matrix, you will land onto p. So p is basically projection matrix into b, right? So you have any vector that is not in the column space or the vector space. So you have a projection matrix, so you multiply your projection matrix with that particular vector and you get your desired projection. So if I do some grouping on this equation, you will see that I get p equals to a transpose divided by a transpose to a to b, right? So as these are dot products, there is no problem in doing this, there is no harm. So this part can be called as the projection matrix, as we have this equation. So our third goal is achieved. So we can say that P or the projection matrix is basically A transpose divided by A transpose A. We'll see some characteristics of this projection matrix. So there might be two special cases while finding out the projection. Okay, what would be the special cases? So let's write it here. Two special cases. So the first special case is when B equals to A. So when B equals to A, what do you get from here? So if you plug, so that means these two straight lines are basically just one or the same. These two straight lines are same. So in that case, do you find any projection? Answer is no, because you cannot find projection of a straight line onto itself, right? So like if you the whole straight line would be the projection in that case, right? So let's draw it. So yeah, so if you have this straight line and you want to find the projection of this straight line onto itself, then you basically own the whole straight line, right? You basically own the whole straight line. So if you switch the values here, so x cap equals to B transpose B divided by B transpose B equals to 1. So as I said, you get the whole straight line. And what about B is perpendicular to A? So if B is perpendicular to A, that means A transpose B equals to 0. Their dot product is 0. So switching this value onto this equation, you will get 0 divided by A transpose A equals to 0. So these are two special cases. So yeah. So now coming back to the projection matrix. So one associated question with this is, what is the column space of this matrix and what will be the rank? So the column space of this matrix, so as you can see that this matrix is associated with the straight line that goes through the origin, like this one. So the column space of this matrix would be A, which is a straight line that goes through the origin, and the rank of this matrix is, as this is a line, the rank would be 1, right? So this characteristic of projection matrix is true only for the straight line case, right? So if I give you any line A, then can you find the projection matrix for it? Answer is yes, you can do it with the help of this equation. You get a projection matrix. So what if, think about this equation, what if A is doubled? If A is doubled, let's switch back to the picture. Okay, so if so the value of A, or this straight line A gets stretched twice, then does it influence the projection? The answer is no, because we are not changing the value of B here, right? So we are just stretching A, which has no effect on this part P. So if you doubled A here in this equation, you can see that you get 2 into 2 4, and 2 into 2 4 in both in both up and down. So like it gets nullified. So the projection matrix doesn't change, the projection doesn't change. And what if you find, or what if you do the projection twice? That means you find P square. So what would be the change in P square? So if you project something on a plane twice, it doesn't necessarily change the projection, right? So similarly, if you find, or if you multiply this P into P, you will see that it stays the same. A transpose A, then A transpose A. So it basically stays the same because yeah, so it basically stays the same. So P square is basically P, okay, equals to P. So and also P transpose is also equals to P, because if you transpose both part of the equation, P transpose equals to A transpose divided by A transpose A. If you transpose the whole thing, you will get the same thing, P. So P transpose is equals to P as well. So these are some characteristic of the projection matrix P. So this was for a line. So we found the projection onto a line. So what about projection onto a subspace? So projection onto subspace, and this is more aligned to our goal today, because we, as I said, that you have a matrix A, so it has some column space. Okay, so let's say you have a matrix A, it has some column space. Let's say this is the column space, let's say this is the origin, and let's say you have this particular B, which is not necessarily in the column space of A. So this is column space of A. Alright, so this line goes outside of the column space. So now you need to solve Ax equals to B, but there is no solution, so you try to find a approximate solution. So what you do is you basically find the nearest point from B to P here. So this is P, so this is the nearest point. So you try to find X that goes to this P, okay, and there is some error here, that is the difference between B and P. So E is basically B minus P or B minus Ax cap. Alright, so which is perpendicular to the subspace or the column space here. So as you can see, it actually creates, so this error vector E actually creates a 90-degree angle with the whole subspace. So you can say that this whole subspace is basically perpendicular. Sorry, so this whole subspace, that means the column space of A, is perpendicular to the error vector. That means the dot product is 0. So this can also be written as A transpose E equals to 0, and E is basically A transpose B minus Ax cap equals to 0. Right. So this is a very familiar shape, so it can be written as A transpose B minus minus A transpose A x cap equals to 0. So from this you can find x cap equals to A transpose B divided by A transpose A, which is also written as A transpose, then A transpose A inverse x cap. Sorry, it shouldn't be here, it should be B. Okay. So yep, so what is the projection? So the projection small p is basically A x cap, which is A transpose A inverse, A transpose A inverse, and I'm taking the A transpose here, so it should be A transpose B. Oh, I think I did a mistake here, so it should be A transpose A inverse, then A transpose B. Yep. So this is X, this is P, and the projection matrix P is basically this one, this part here. That means, so PB is equals to P, so P is basically the projection divided by the B. So if you divide this part, this whole part, divide with B, you will get A into A transpose A inverse A transpose. Yeah. So these are the goals. That we work with. So what is the practical problem for this? So let's say you have a matrix A that is 1 1 1 0 1 2. Okay. So this has some column space, and you have any vector B that is 6 0 0, that is not inside the column space of A. Alright, so you need to project, so you need to find what is the nearest point of B on the column space of A. Okay, so you need to find the x cap, you need to find the projection P, and you need to find the projection matrix P. So that is the ultimate goal. So let me summarize it. So in real life scenarios, in most of the cases you cannot find Ax equals to B. Okay, so when you cannot find Ax equals to B, you try to find the nearest point of B onto A. So that's where you solve Ax cap equals to P, right? So what are the steps for solving this? So the steps for solving this is you multiply both sides of the equation with A transpose, and whenever you multiply both sides of the equation A transpose, then you get a solvable scenario. Okay, so then you get x cap. So you find the x cap from here, so you get A transpose B divided by A transpose A, which is A transpose A inverse then A transpose B. So as you have found the x cap, then you multiply with A and you get the closest point, that means the projection onto the subspace or the column space of A, and you will from this you will get the projection matrix P. Now why, first of all, why this is important? I mean, why do you try to find out the why do you try to find out the nearest point P? Okay, what is the point of finding out the nearest point? So the point here is, let me tell you a real life scenario. Let's say there are some houses in an area, okay, and there is one feature of those houses. So there are some houses in one area, and there is one feature of those houses, and let's say that feature is number of rooms. So if you try to draw it in a linear number system, so you have one feature for one room, one house, that is number of rooms, and that is not linear. Okay, so the if you have two rooms, let's say the house of the the price of the house is 2 million, but if you have three rooms, the price of the house is, let's say, 2.2 million. So as you can see that this relationship is not linear. So if you try to picturize this onto a grid, you will see that if this is this axis is for price and this x-axis is for number of rooms, then you will see that you will get different points on different places, right? So if someone asks you that to define a model for predicting the houses, that means if I tell you that if I have 5 rooms in a house, what should be the price of that house? Or if I have 8 rooms in a house, what should be the price of that house? So this is like a machine learning model where you try to predict something, right? So I have given you some data: 2 rooms 2 million, 3 rooms 2.2 millions. So these are called features and these are called labels. Okay, so after that, after feeding you with the data, I am giving you one query and asking you for a prediction. That's what machine learning does, right? So what you do, you try to find a linear line that best describes this relationship, rooms with the price of the house, right? And what you do is that, as you can see, that this this straight line is not perfect. So what you do, you try to find the errors. You try to find the errors here, E3, E4, and you try to minimize it. you try to find the errors and then you try to minimize the errors so that your straight line goes very close to all the points, so that you make the best prediction. All right, so that is where the idea of, so as you can see that whenever you are working with errors, you are basically projecting these points onto these lines, right? So this is where the idea of projection comes from, and this is why this is very important in all the applications of data science and linear algebra, machine learning, these sort of things, right? So I'll further explain it in the classes. I know I couldn't explain it very well, so I'll do it in the next class, inshallah. So yeah, so I have one task for you, that is, you have A. I have in fact written it here, so I'll again write it, no problem. So you have this matrix A and you have this vector B, and that doesn't really fit inside the column space, so you have to find the x cap. You have to find the x cap, you have to find the projection, and you have to find the projection matrix, these three parameters. All right, so solve it and submit it with the, so you have all the equations here. I have written all the equations for this, and I'll submit it with the assignment, and I will ask someone from the next class to solve it during the class term. Thank you for your patience. Assalamu alaikum.